So again, thank you all for coming. This is, as Adam mentioned, a very, very long awaited occasion. I will be investigating paleoceanographic changes along the Permian-Triassic interval, along the northwestern margin of Pangea, specifically looking in Opal Creek, Alberta, Canada. Now, giving a background into what's going on, we first will be starting out with the Permian, as we see here. So during the Permian, we are within the late Paleozoic ice house. So we see that there's a massive continental ice sheet along the South Pole. Pangea itself is situated more within the southern hemisphere. And with this continental ice sheet, we also have active thermohaline circulation and coastal upwelling. Moving through the Permian, we have one of the biggest events in geologic history, and that is the late Permian extinction event, which occurred roughly 252 million years ago. It is the largest of the mass extinctions, resulting in approximately 90% of marine genera and 70% of terrestrial genera becoming extinct as a result of the happening, so to speak. Causes for the late Permian extinction, the Siberian trap flood basalts are considered the primary driver of environmental hardship for the extinction itself. And from the eruption of the Siberian trap flood basalts, we get a variety of additional stressors, all related to this eruption. So we go to extreme global warming, and with that, we move into the release of methane from seafloor clathrates and inevitably ocean stratification and reduced benthic oxygenation as well. And here is a nice little comparison in this dark charcoal. We see the extent of the Siberian traps, and for reference, for we in the United States can see how large of an expansive area that it covered. It's roughly probably like almost a half to 2/3 the size of the United States. All right. Moving on from the late Permian mass extinction, we move into the early Triassic. At this point, obviously, we are dealing now with the aftermath of the late Permian extinction. Pangea as a whole has shifted northwards. We no longer have the massive continental ice sheet over the South Pole, as we now have a transition into more extreme global warming with increased surface sea temperatures and, again, ocean stratification and deep water anoxia. Right, so before we get into our work of what's going on, we want to look into previous works that have happened, that have been researched into the Permian-Triassic interval itself. Paleo-environmental changes from the Permian to the earliest Triassic were previously examined by Schoffer et al. 2013. And Schoffer assessed, essentially, stratigraphically, he looked around 10 meters below the extinction to 25 meters above the extinction or event horizon itself. So he has this pretty in-depth window of what's going on. In their results, Schoffer noted that during the Permian, we do have high productivity, and we have oxygenation that is being driven as well by this high productivity. Moving into the Permian, obviously up into the late Permian mass extinction, we have a collapse of primary productivity, and then within the early Triassic, productivity continues to be hindered, and to the very top of their study section. And so Henderson hypothesized that productivity essentially continued to be hindered throughout the remainder of the early Triassic. And to essentially illustrate all of these, this information, Schoffer developed a 3-step model to illustrate how the slow deterioration of these environmental changes led up to the extinction and slight window of the aftermath of the extinction as well, which we have here. So for A, we go from middle to late Permian. And so this is middle to late Permian. We have upwelling along the coast of oxygen-rich bottom water. It's also nutrient-rich as well. And this upwelling of nutrient-rich and oxygen-rich water is basically causing the boom of productivity that we see along the coastline, and that Schopfer noted in their study. Moving into the latest Permian extinction interval, just prior to the extinction interval itself, we're seeing now that that they're still upwelling, and now we have an increased amount of continental erosion and nutrient runoff that's leading to massive eutrophic events. And we also have an expanded oxygen minimum zone from the amount of consumption and decay of productivity. And followed into the early Triassic, at this point, now upwelling has ceased to exist. Bottom waters are suboxic, and the limited productivity that is seen in Schopfer's results is essentially confined to runoff from the continent. Oops, I pushed that button. There we go. All right. In addition to Schopfer's work, we also looked at some other works from very talented scientists. From Beauchamp and Bod, in their study, they looked at early Permian chert deposits that record the collapse of large silica factories due to the near cessation or near termination of coastal upwelling along the western margin of Pangea. So closely tying into what Schopfer discussed for the late Permian. Algae and Twitchett note that within the earliest Triassic, there's a short-lived pulse of high primary productivity, and that it was due to increased terrestrial weathering. Graysby took primary productivity and assessed it across the interval itself, and saw that primary productivity was actually reduced due to a deep thermocline created by the extreme global warming that the planet was experiencing during this transition. Wignall and Twitchett assessed widespread ocean anoxia during the latest Permian and into the earliest Triassic. And finally, Beatty looked at trace fossil assemblages from the lower Triassic rocks and used them to define what we have come to know as a habitable zone. And so the habitable zone is actually a model that is useful in trying to assess conditions for recovery. So here we have the model for Beatty, with Schopfer insinuating that the rest of the Triassic is low productivity, and Beatty is now coming in with this model looking at productivity actually being sustained, but at shallower depths, and being sustained via aeration from, obviously from crashing waves and from nutrient input from terrestrial sources, and within the range of fairwater wave base and stormwater wave base. And specifically that's the very base level of water that is affected during specific conditions, so that would support life. We do note that the Opal Creek section is actually is laterally not translative, but it's equivalent to where the Hood Creek Formation is at. All right, so now comes our research objectives. First and foremost, we want to assess primary productivity, oxygenation, changes in sedimentology, and changes in sedimentology during the Permian, and determine if productivity collapsed at the end of the Permian, as suggested by Beauchamp and Bod and Schopfer. We will also be looking and assessing if primary productivity continued to be dampened in Northwest Pangea following the Permian-Triassic extinction, suggested by Schopfer. And then finally, we're going to assess as a whole, assess and reconstruct paleooxygenation, primary productivity, and changes in sedimentation within the Eastern Pathalassic Ocean from the late Paleozoic icehouse during the Permian to extreme global warming during the Triassic. Essentially, we are extending the study site from Schopfer's initial study. Okay. All right. So where exactly this is all happening in relative to, in relation to back in the good old day of the Permian-Triassic boundary. So the red star here denotes where Opal Creek is approximately. We see that to the west, we have the Pathalassic Ocean, which essentially wraps all the way around to the east coast of Pangea as well. And the Thesis is a nearly enclosed sea within the eastern margin right here of Pangea, or east of where our study locale is at. Getting a little bit of a more zoomed in look of where our study section is at. Specifically, Opal Creek the Opal Creek study section is located within the Acase Valley in Alberta, Canada. It is southwest of Calgary. So here we have where the Acase Valley is in relation to LA. And here is the Opal Creek study section that we assessed. All right, so Opal Creek. Why Opal Creek? So Opal Creek in itself is a well-exposed and nearly complete stratigraphic record of marine environments across the Permian-Triassic interval. It is deposited primarily in a continental shelf setting along the western margin of North America. And our study section includes the following units that we will be essentially investigating. So we begin with the early Permian Johnson Canyon Formation, then move into the middle Permian Ranger Canyon Formation, and then finally representing the lower Triassic or early Triassic, we have the uppermost Permian to lower Triassic Sulphur Mountain Formation. Now the Sulphur Mountain Formation is in our study is further subdivided into the early Grisbackian Phroso Siltstone member, and then the late Grisbackian to Spathian Vega Siltstone member. And over here we have a beautiful strat column that y'all can gawk at it, or you can email me if you want to see it up close. All right, sampling for the study itself. So 230 hand samples were previously collected from Opal Creek at a 1 to 1.5 meter interval over the cumulative thickness of 330 meters of the study section. Specifically around the Permian-Triassic boundary, samples were collected every 10 centimeters within a meter above and below the boundary itself. And these samples were collected previously. I unfortunately was not able to go. I wish I did, Adam, but it's okay. I will be more than happy to give this presentation instead. All right, geochemical analysis of Opal Creek. So what we did was that we took our hand samples and then powdered them using modified version of, and prepared them using modified version of the flux fusion method by Murray et al. 2000, and analyzed them via ICP-OES. Using the ICP, we conducted elemental analysis with the following elements. So to assess productivity, we used barium, copper, nickel, zinc, and phosphorus. To assess oxygenation for Opal Creek, we used vanadium and molybdenum. And finally, to assess sedimentology for Opal Creek, we used calcium, magnesium, titanium, zircon, aluminum, and percent total organic matter. Specifically for percent total organic matter, these samples were prepared for loss and ignition using Dean 1974. to determine, again, said percent total organic matter. Finally, trace element data is normalized using enrichment factors using the equation from Triboviard et al. 2006. And we normalize trace elements to essentially make it a little bit easier for us to determine whether or not our study section or portions of our study section is either enriched or depleted in a specific element. And for that, for enrichment factors, we specifically looked at barium, copper, nickel, zinc, vanadium, and molybdenum. And here we have a picture of an ICP-OES. It is not the one that's at CSUF. Fortunately, I was not able to take a picture of the one at CSUF. I am sorry, but here's one anyways. All right, so after toiling with 230 samples, here is where we are. And so in this first column, we have our plotted results for productivity. This middle plot right here are our oxygenation proxies. And then finally, at the very end, we have our proxies that we use for sedimentation, along with their relative position to each associated unit for Opal Creek. So I could give y'all 15 minutes to an hour to decipher this entire thing, but then that wouldn't be as much fun. So I'm just gonna go ahead and just break this down for y'all section by section and make it a little bit easier. So first, we'll break it down into the bottom-most units. So beginning in the Permian, we're gonna start off with the Johnson Canyon Formation, denoted down here in the red box. So it's so much easier to read. Johnson Canyon Formation, we're looking at lithology, productivity, oxidation, sedimentology. And so for the lithology of the Johnson Canyon Formation, we're looking at light gray laminated Shirley dolostones with abundant nodular phosphate layers. There's a little image of a cliff face of the Johnson Canyon Formation. Overall, for productivity, we see that copper and zinc is enriched throughout the Johnson Canyon Formation. For oxygenation, vanadium is initially depleted and then becomes enriched above the 15-meter mark here, or the negative 15-meter mark here. So we go from depleted to enriched. And then finally, for sedimentation, titanium and aluminum are overall, they're just low for what we would compare for in later sections. Click the button and now it's not going. There we go. All right, next we will be moving into the Ranger Canyon. The Ranger Canyon, we would also be looking into the late Permian mass extinction, as well as the Permian-Triassic boundary, just giving a little tidbit about what's going on within that department. So for the Ranger Canyon Formation specifically, we have within here this lovely little section. In terms of lithology, Ranger Canyon Formation is a recrystallized gray, blue-gray speculated chert, silicified sandstone, and phosphatic siltstone. Here we have a nice example. For productivity, we know that copper and zinc are still enriched, but to a lesser extent of what we saw in the previous Johnson Canyon Formation. For oxygenation, vanadium is roughly around 1 in value throughout the entire unit. And finally, for sedimentology, we see that aluminum and titanium contents become elevated with the deposition of the deposition of the Ranger Canyon Formation, excuse me. And for the extinction interval, the most notable thing that is going on is the changed in lithology. We moved from this recrystallized spiculated chert into a black organic rich fissile shale for the Phroso siltstone member. And for analysis for the remainder of these elements, I will be discussing that a little bit later on. Right. Next, we have the Phroso siltstone member right here. So one thing to note is that the Phroso siltstone member acts as both the base of where the late Permian-Triassic, the late Permian mass extinction event occurs, and also houses the Permian-Triassic boundary. In total, looking at lithology for the Phroso siltstone member, we're looking at black, organic, rich, fissile silty shales that completely lacks bioturbation and or distinct trace fossils, and also lacks any benthic macrofauna. For productivity, we see that copper and zinc enrichment factors fluctuate throughout the entire unit. Looking at oxygenation, again, vanadium enrichment factors are roughly around 1 throughout the entire unit. And finally, for sedimentology, consistently elevated aluminum and titanium content throughout the unit, much to what we saw in the Ranger Canyon formation. And finally, we have the largest of the units, which is the Vega siltstone. So the Vega siltstone member, in terms of lithology, it is a gray to dark gray, sandy to silty shale with trace fossils and ligula. And for productivity, we're looking at copper and zinc. Enrichment factors are consistent throughout the unit. So unlike the the Phroso siltstone member, which is fluctuating, now we're moving into a more stabilized copper and zinc values. Oxygenation, we see that vanadium is depleted throughout the entire unit. And for sedimentology, again, consistently elevated aluminum and titanium content. So looking at all 4 units, what exactly does this all mean? So let's give a little explanation to what's going on. For productivity, enriched copper and zinc enrichment factors, and along with nearly identical trends between copper, zinc, and phosphorus, all this essentially equates to the Johnson Canyon having high primary productivity, or high productivity in general. For oxygenation, depleted enrichment factors that transition to, that then become enriched, shows that there's a shift to anoxic conditions, which is most likely from eutrophication. And with sedimentology, low levels of titanium and aluminum essentially just equate to low detrital input during the deposition of the Johnson Canyon formation. Here we have a model much to, or similar to that of Schopfer, just with a little bit of tweaking, showing now, instead of the middle to late Permian, we're now looking at the early to late Permian, so nearly the entire Permian in its entirety. So here again, with high primary productivity, and low nutrient input, we have evidence that there's upwelling, there's a strong upwelling that's going on between the early to Permian that is supporting high primary productivity. We also get some, and it's slow deposition of sediment, and we have some sponge reef facies. Moving on to the Ranger Canyon formation, this is where we can give insight into the Permian, into the late Permian extinction interval itself. So first off, for productivity, copper and zinc are again, still enriched. And so that essentially means that we have high productivity again, but to more less of an extent than what we observed in the Johnson Canyon Formation. And looking at the extinction interval, we have a brief collapse of productivity due to the extinction itself. For oxygenation, vanadium, we see that with it being around a value of 1 for here, we note that it goes from oxygenated to anoxic. And looking at the transition for the extinction interval as well, it's just continued anoxic conditions across the extinction interval as well. Sedimentation, we see that these elevated aluminum and titanium contents mean that for the Permian specifically, it is a condensed section and it's due to the large input or large detrital input that we see here with the increase in titanium and aluminum. And so our model that was drafted shows that now we have weakened upwelling because we still have primary productivity, but to a more less of an extent as we observed in the Johnson Canyon Formation. We now have rapid sedimentation from increased continental runoff and continental erosion and runoff. And this is noted with the lithology because we moved from a gray spiculate chert to now a more silicified like sandstone and siltstone for the Ranger Canyon Formation. All right, moving on, Phroso siltstone member. For productivity, we have that it is productive. However, it is not to the same extent, again, as we saw in the Johnson Canyon Formation. And with copper and zinc enrichment factors fluctuating, that tells us that we have variable productivity during the deposition of the Phroso siltstone member. For oxygenation, again, with vanadium enrichment values at around 1, that means that we are looking at anoxic conditions during the Phroso siltstone member. And finally, for sedimentology, a consistently elevated aluminum and titanium essentially means that now we have sedimentation from runoff. So it's a lot more from runoff. Here we have now, after the late Permian extinction interval, moving for C, we have early to middle Brisbachian representing the Phroso siltstone member. So we have at this point terminated upwelling, and so we have a stratified ocean to top that off. Fluctuating productivity, and from it's consistent continental erosion and nutrient runoff, but again, we have that fluctuating productivity that we see in our data. And last but not least, we have the Vega siltstone member. So productivity within the Vega is stable. So we look at productivity being moderate, but it's enriched, but it's not to the same, again, not to the same extent as what we saw within the Johnson Canyon Formation. For oxygen, we have values that are less than 1. And so that tells us that our environment is oxygenated. For sedimentology, same as what we observed within the Phroso siltstone member, of consistently elevated aluminum and titanium content means that we, again, have sedimentation from runoff. And here is the model of what we can assume is what's going on. Again, we still have abatement of upwelling and a stratified ocean. And now based on our data, we have productivity that has been restabilized or reestablished and is being supported by consistent continental erosion, and nutrient runoff. So what exactly does this all mean? Essentially what's going on is that cold water upwelling led to high productivity during the height of the late Paleozoic ice house during the early Permian. For the Ranger Canyon Formation, it is a condensed section that represents the waning phase of the late Permian ice house, with increasing global temperatures leading to the decline of the strength of upwelling and productivity that we saw within our data. And this and our results actually differ from those published from Schopfer, who shows that there's no decline of primary productivity over that same interval. Contact between the Ranger Canyon Formation and the Phroso Siltstone member marks the boundary of the late Permian mass extinction or the Permian-Triassic mass extinction, and represents an unambiguous establishment of anoxic conditions within the region. Next, we have barium, copper, zinc, and nickel enrichment factors. These values decrease sharply, rapidly just above the Permian-Triassic event or the late Permian extinction event, and record the collapse of primary productivity. Moving on, we have a quick or swift increase in copper and zinc, similar to those of the Ranger Canyon Formation. So this is moving into the just after the late Permian extinction. So a swift increase in copper and zinc values, similar to those that we saw in the Ranger Canyon Formation, record rapid restoration and gradual strengthening of productivity following the extinction. And this actually is, this records a similar drop in productivity that Schopfer saw within their results, but their post-extinction recovery is more relaxed, or their post-extinction recovery is more relaxed comparing to what we noted within our data. Next, we have high aluminum and titanium contents indicate that there's an increase in terrigenous input around the time of the Permian-Triassic extinction or the late Permian extinction, used interchangeably, due to the denudation of continental environments by the mass extinction, and that's support for Algeo and Twitch's hypothesis. While the organic rich nature of the sediments deposited following the extinction itself may be due to a much larger influx of terrestrially derived organic matter. Phroso's Siltstone member and of the Sulphur Mountain Formation is deposited in a deep water distal shelf setting under persistent anoxic conditions. And this, for the Phroso Siltstone member being deposited within these type of conditions, this is even more evident with it being a black organic rich silty shale with no bioturbation and no other trace fossils found within it. Fluctuating fluctuating copper and zinc enrichment factors indicate unstable productivity that was likely driven by runoff during the deposition of the Phroso Formation. And that's based on consistently high aluminum oxide and titanium contents. And finally, I believe, we have that the Vega Siltstone member records a middle to proximal shelf setting deposited in a relatively shallow environment compared to the Johnson Canyon, Ranger Canyon, and Phroso Siltstone members, and took place under more oxygenated conditions. And looking back at referencing back to our model for the Vega Siltstone member, we see that productivity is thought to be within a more shallow environment. So we can assume that this is also within the habitable zone as described by BD et al. 2008. For results of the study, it points to the importance of terrestrial runoff in delivering nutrients to shallow shelf settings during a global hothouse. Anoxic conditions during the Phroso match similar data from the Permian-Triassic boundary, at least within the Grisbakken for Wignall and Twitchett, that they essentially assessed in, Wignall was in Ursula Creek. And so matching their, or having similar results to their findings, this provides further evidence of widespread anoxia or anoxic conditions during the Permian, Permian-Triassic mass extinction. And finally, the Permian and early Triassic sedimentary sequence preserved at Opal Creek section records a pretty severe shift in climate as we move from the late Paleozoic ice house to an extreme hot house in the early Triassic. And thus this resulted in the most devastating of mass extinctions in Earth history. Our planet has experienced a similar shift in climate change, but over a much shorter temporal scale as a result of anthropogenic processes. And so the results of this study can hopefully illuminate and illustrate a potential future for the Earth should current rates of anthropogenic warming go unchecked. So hopefully it's a wake-up call for humanity, but we'll see. And on that note, I want to thank so many people. I do want to thank my thesis committee, Sean, Joe. I didn't have a photo of y'all, so I couldn't put you in. I'm very sorry. It's like not that many photo opportunities. I do really want to thank Adam for putting up with me for 7 years as both an undergrad and a graduate student. And there are just so many people that I want to thank. Obviously, my mother, my godmother, my friends. I don't know if she's watching, Claire, the entire Dean of Students team, for even though it was student affairs, y'all provided so much support during this entire ordeal. All my besties that are on here, you know who you is. If I didn't picture you, I'm sorry. It is most likely that I don't have a picture of you, or that the picture is not really something you want to see in public. But on that note, all I can say is thank you. And if you have any questions.
All right, Anthony.